Now let's talk about another method for determining convergence and divergence in series, which is the integral test. And to use the integral test, we have to meet four basic conditions, which are these four. The first one is that f of x, which is going to be the function that's going to be in the integral, is equal to a sub n. So we have the series from, let's say n equals 1 to infinity of a sub n. Well, we need our function to match whatever is in here. The next condition is that f of x needs to be greater than 0, and the integral just does not work if our function is less than 0. The third condition is that f of x is decreasing, and this isn't really hard to show. Basically, all you'd have to do is show that the derivative of f is less than 0. And the last one is that the limit as x approaches infinity of f of x is equal to 0, which means f of x approaches 0. And that is very similar to the nth term test. So basically what's going to happen after these conditions are met is that our series is going to follow the integral. So if the integral of f of x dx converges, then the series, the sum of a sub n, will converge as well. And likewise, if the integral diverges, then our series will diverge as well. And let's see why that is. So let's assume f of x, our integral, diverges. Well, we're talking about from n equals 1 to infinity of a sub n. So we can graph this out, where this line right here represents f of x. So I've marked out different intervals, and these are going to be our different n's. So what we want to show is that our series is greater than a diverging integral. And if we can show that, then we can prove that our series diverges, since it's greater than something that diverges. Well, to do that, we basically just need to take a left-hand sum, because left-hand sums are greater than the function, or than the integral. As you can see here, these are the left-hand sums for a sub n. And the area right here, well, that's just going to be a sub 1, right? Because we're taking the area, 1 unit, and the height of a sub 1. This is just going to be a sub 2, a sub 3, a sub 4, and that goes on forever and ever and ever. And as you see, this area right here shows us that it is greater than the integral. And since the integral diverges, we're assuming this, our series will diverge as well. Now let's look at a converging integral. So we're assuming that now f of x, the integral of f of x, converges. So remember, our series is from n equals 1 to infinity of a sub n, and here's another graph of f of x. Well, to prove that it converges, that this series converges, we have to show that it is less than a converging integral. And when we want to take sums that are less than the integral, we take right-hand sums. But since we're starting at 1 and we want it to be less than the integral, our right-hand sum is just going to look like this. And our first term, well, this is an a sub 1, this is now a sub 2. And this is a sub 3. This is a sub 4, this a sub 5, and that goes on and on and on. And this area right here shows us that it is less than a converging integral. So that doesn't show us that this whole thing is less than the converging integral, because we're starting at a sub 2. So what this is telling us is that the series from n equals 2 to infinity is less than our integral. Well, we're starting from here, from 1 to infinity of f of x dx. So that proves that the series from 2 to infinity converges. Well, basically all we're doing now is adding this first term to get the series from n equals 1 to infinity. Because to get from 1 to infinity, when we're starting with 2 to infinity, all we have to do is add the first term. And the first term, that's just going to be a real number. So if we're adding a real number to something that converges, well, that's still going to converge. So that's why the series will converge if the integral converges. But what this can tell us is also the error bound of our series. And basically what happens is, since this is true, we can go ahead and add a sub 1 to both sides to get, well, if we add a sub 1 to the left side, this is just going to start from n equals 1 to infinity. And that's going to be less than the integral from 1 to infinity of f of x dx. And that, well, we added the first term to each side, so that's just going to be plus a sub 1. And that's going to be the upper bound. And the lower bound, well, what we can tell is, well, if this is less than the integral, well, then our lower bound will just be the integral itself. So the integral from 1 to infinity of f of x dx. And I'll rewrite that again a bit nicer. So what we proved just then is that our series from 1 to infinity is going to be less than our integral from 1 to infinity, this is a sub n, plus our first term, and it's going to be greater than the integral by itself. So we just proved two things in this video. The first thing is that our integral is going to follow, our series is going to follow the integral. So if our integral converges, the series will converge. If our integral diverges, our series will diverge, because we can prove that it's either greater than or less than the integral, whichever way we want it to. The second thing we showed is that there's an error bound, which is that the series is greater than the integral, but less than the integral plus the first term.